and welcome to Drilling Insight. I'm Jeremy Verduzco, host and editor of National Driller magazine. I'm joined today by drilling trainer, National Driller writer, and co-host Brock Yorty. How's it going, Brock?
Doing good. How are you doing, Jeremy?
I'm doing excellent, very excellent today. And joining us on today's show is Professor Reed Maxwell. Thanks for being on the show, Reed.
Thanks so much for inviting me. Really appreciate the chance to talk to you guys.
So, Reed Maxwell is professor of civil and environmental engineering and the High Meadows Environmental Institute and director of the Integrated Groundwater Modeling Center. He's all of that's at Princeton University, and he's also this year's NGWA Darcy Lecturer, which focuses on groundwater and the water cycle. So let's jump right in with our usual opening question. So Reed, did you choose this industry, or did it choose you?
So I actually have 2 degrees in mechanical engineering and 1 in civil. And I've always been into fluid mechanics, and originally I wanted to do like air pollution type stuff, fluid mechanics, air pollution. And it was just kind of a twist of fate that I ended up in environmental engineering. The master's advisor that I started working with at UCLA, and we worked out fine, but her environmental work had dried up, and I was doing transverse mixing in supersonic crossflow behind a rearward facing step was the title of my master's thesis. It was supersonic combustion kind of stuff, which is interesting to some people, but it wasn't, it was, kind of not quite bait and switch from environmental engineering.
I think I fell asleep halfway through that title.
I think I fell asleep just telling it to you. Yeah, so I, shopped around and found an advisor who was really into environmental stuff and finished my PhD, did my PhD at Berkeley in civil environmental engineering and water resources, got into water, and, all the fluid mechanics background was great. It was really a nice fit, and it just kind of like, clicked with me that that's what I wanted to do. So I guess it's kind of both. I always kind of wanted to do environmental stuff and was interested in movement of fluids, but just didn't realize it was water. It was water came around and, kind of brought me in.
Well, we're lucky you chose water. Okay, what is the Integrated Groundwater Modeling Center, and how might it affect us crazy tribal industry drillers and the groundwater supply industry?
So the Integrated Groundwater Modeling Center, or IGWMC, has a long history, and I only took over as director about 10 years ago. And I have to thank Professor Emeritus Eileen Potter, who is an amazing director who really kind of handed me the center in this great shape, and and allowed me to kind of put my vision on it. So what the center has done for a long time, and a mission that's really near and dear to my heart, has been a lot of tech transfer, and we've taken that as education outreach from the K-12 undergrad all the way through to the professional level. And so it also houses a lot of research. We do a lot of hydrologic modeling, groundwater surface water interactions. That's a big part of what we do, and it provides support and infrastructure for students and such. But I think one of the really neat things about it is this really education at all levels. So we put on the Mod Flow and More conference, which is the largest applied hydrologic modeling conference in the world. Usually every 2 years. We're actually gonna have to skip a year because of the pandemic, so it's gonna be in 2021, fingers crossed. But we've had really tremendous success with that. We have a lot of people, about 350 people usually come every other year. We have very focused, really neat spectrum between research and applied, and this really nice tech transfer. And then we put on a ton of short courses, some of which have, for different societies, have professional recertification type credit. Again, kind of span the range. And then we have a big education outreach program and a dedicated full-time director who helps manage and run that outreach program. And we bring in money from National Science Foundation, from Department of Energy to help sort of support that. So in addition to research, in addition to sort of, focal point around hydrologic modeling, groundwater modeling, we also have this really neat education outreach at a whole broad range of levels.
So really focused on both education and application, you know.
Yeah. Yeah, really,
Okay.
I think it's a neat mission. That's a really, and as an academic, you know, if you don't, research is a big part of what I do, but teaching is also a huge part of what I do. And teaching takes a lot of different forms and a lot of different levels.
Mhm. So how does the kind of modeling that the center talk about, like the kind of modeling they're talking about, how does it affect withdrawals, particularly for the kind of large scale water consumers that,
Well,
Yeah.
you know,
yeah,
some of
we
the
do all
companies that
scales
are,
though. So
oh,
we do
go,
everything from really small scales. We do everything from really small scales, you know, all the way out to really large scales. So I think this is one of the challenges in hydrogeology is that, you know, so much of what, you know, so much of the way that we see groundwater through wells, through, you know, pump tests, through producing, through, you know, contaminant transport issues, gets at small scale heterogeneity, gets at, you know, intermediate scale, if you want to call it, hydrostratigraphy, and a lot of these real kind of issues. But so much of the big picture management, so much of the interactions happens at larger scales. And that's just a challenge, right? To bridge something that's meaningful at the individual pump test scale where the screen matters, the local heterogeneity matters, fractures matter, you know, all these small details matter. But then, you know, thinking about how this fits in context with, okay, how are we going to manage groundwater? How are we going to manage groundwater and surface water? How are we going to think about replenishment in wet and dry years? These are bigger picture kind of issues. And so it's tricky to bridge those scales. And that's what a lot of my work has done. And that's what a lot of the center type work has done. And that's been a, you know, big underpinning, sort of the focus of, or themes from two of my Darcy lectures.
Mhm. So really, I mean, you rebutted me a little bit there, but it's really about the whole system is what you're saying, not large versus small versus medium versus,
Yes.
you know, it's
Yeah.
whatever is going in and coming out.
And I didn't mean to rebut you there, Jeremy. I was just sort of, I guess I was like agreeing with you, or maybe agreeing with you up front, or in advance. No, somehow I've been lucky enough to have this a little bit of a random walk in my career.
Mhm.
And I started out really focusing my research on small scale heterogeneity, uncertainty, and in subsurface heterogeneity and different models, often geostatistical, but, you know, using some of the geologic inference too, things that like similar to what Graham Fogg has been championing over his whole career. And then I was lucky enough to take, you know, field classes and such from, you know, some of the greats like Tian Narasimhan, who, you know, is one of the really big names in early, you know, understanding and interpreting what you get out of observations in the field. And, you know, through that process, the small scale really was drilled into me. And then because I went from the small scale up, I think I hopefully haven't lost the appreciation for, you know, when we make these large scale models, yeah, there's a lot that we're, you know, kind of averaging up, and we always want to, you know, always want to pay attention to whether or not that matters. And, you know, when you go into larger and larger scales, which is important, and, you know, a lot of management decisions and a lot of policy happens at these broad brush scales, but you want to make sure how much of this small scale, how much of these small scale details are important, and how much of these do you want to carry along to the large scale.
So in the United States, a lot of water policy is conducted at the state level, correct?
Yeah.
Now, what can we do to streamline, you know, rules that differ a lot from state to state, or is that even a
That's,
smart tactic given
I mean,
different geologies?
I think it'd be a really smart tactic to, you know, but I don't know that we could ever do it. I mean, it's so entrenched. You know, I mean, you look at the differences in the way, say, Colorado and California even discuss groundwater. You know, you buy a house in Colorado and there's groundwater's in your, you know, in your paperwork. It's in the, you know, the whole title packet, and whether or not you have water rights and whether or not these groundwater rights will eventually flow into a stream or not. And that's really unique, and that's very forward thinking. Other states, you know, it's not even part of the conversation, or lumped in with surface water, or they're totally separate. And so I think there's this really big, you know, really big divide in terms of how you know, even surface water, but let alone groundwater is thought about and managed. And I think it would be really, really great to have some kind of standardized way to manage it. But you know, frankly, I don't see it happening. I mean, and I'm an optimist. I'm really an operational optimist. But I mean, I think it'd be great. But I think, yeah, I don't know. I mean, it's a terrific question.
Yeah. Well, what just to digress a little bit, I mean, what do you think that model might look like? Or what do you think a baseline set of water management rules across that cuts across all of these different municipalities would look like?
Yeah, I mean, I think it's very interesting because I think that if you look at a couple of the different views, there's the view that, you know, surface water and groundwater are two different buckets, if you will, or, you know, a bucket and a piping system, and that they don't connect at all.
Mm-hmm.
Then there's views where all groundwater is just waiting to be surface water. And it's, you know, and so it's sort of like if you're pumping groundwater, then you're taking water from some downstream user. The truth is in between, right? And the truth varies so much across the country, and depends on climate, depends on, you know, the hydrostratigraphy, depends on the topography, depends on, you know, vegetation. There's so many factors that go into this. And I think first we need to kind of understand, and not just because there's been a lot of research on that across a broad range of scales. And I think in the big picture, I think we have a pretty good understanding of these things. But I think that making it and communicating in a way that we all, you know, everybody could say, okay, I get it. I get where, you know, groundwater is maybe totally separate, but this groundwater is, you know, recharged under a whole different, whole different climate system. Whereas this groundwater is, you know, basically was rainfall pretty recently and is going to be stream flow also relatively recently, and understanding and how to communicate that. Because I think it varies a lot. And I think we tend to, just tends to be hard to visualize. Groundwater's out of sight, out of mind, right? It's hard to, you know, even for scientists, let alone the public and decision makers. And so I think that's one of our challenges. I think it's as much a communication challenge as anything.
It seems like we only get to standardization on this when it goes to the Supreme Court, like with Texas and Mexico that just happened, or, you know, we have this expectation, but then the only way it gets there is the highest court in the land.
Right. Or Hawaii. I mean, there was the Hawaii case was really, and shout out to the great hydrogeologists at UC Davis that provided some really neat briefs on that. But yeah, I mean, I think that you're right. I think you're right. And it is interesting how much, you know, gets pushed to the courts and how much of this gets decided in the courts.
So a big base of ours is obviously the drillers, and that's how we get our field data and our water, but we're stubborn, self-taught, tribal, and we take science and we push it aside sometimes. So as drillers, you know, how can we, like, I've lost my spot here. How do we get them on board with this modeling data, and like, how can we contribute to it?
So I think about this a lot, and I think you hit the nail on the head, because there's so much heterogeneity. It's almost like, you know, once you can cite a location, you can do calculations, you can do so much, but then once you actually drill a well, you find out so many things that you didn't anticipate. And as good as geophysics are, as good as, you know, all of the data sets that we have, we're still really, our basic information is drilling a hole in the ground. What do we see when the mud comes out, or what do we see when we core? What do we, you know, when do we hit water? How well does it flow? Like all of these things, that's still our basic way to understand what's going on in the system. And it's this little pinprick, right? And so it's very localized information. And you know that some kinds of heterogeneity are going to change 10, 20 feet away. And so it, of course, makes this sort of challenge, because you can say, yeah, you can do all this up front, but until you drill in the ground, you don't know exactly where the water table is going to be, or, you know, and I think that we owe it to make this connection between people that are, you know, drilling, that are in the field, that are, you know, really kind of interfacing with groundwater directly. And then what we also know about big picture, and a lot of the work that I do, we're trying to understand how much water do we have at large scale. Now, we're not nearly to the point where we could say, okay, if you pull a location out of one of my models and go drill at that location, there's gonna be a lot of surprises. And it doesn't mean that the model's useless. It doesn't mean that, that the driller shouldn't include understanding of science. It just means that there's so much detail in what we're trying to do. And what we're trying to do is a really hard problem. And there's so much heterogeneity, and locally at the well scale, this heterogeneity matters a ton. At the large scale, maybe less and less. And if we want to think about like large scale water policy, and we want to say, okay, how much should we be pumping in terms of groundwater, and what's sustainable groundwater pumping? These are probably larger scale questions. If we want to say, where should we site that well? Well, that's a much smaller scale question. Or what interval should we pack it off at? And I think we need better feedback, because we need all the data we can get, and we need all the communication we can get, to really understand the whole picture. And I think that it's it's a communication. It's a number of factors. One is communication, and then the other is helping to advance kind of the big picture down and the small scale up.
That's from a data standpoint, drilling's complex. There's a lot of things that happen, and we do a lot of disruption to the model as we're drilling. But if we were to provide better data, what would that data look like, and how could we be more impactful to your modeling system? Like what could we do better as an industry of drillers?
So it would be, and I don't know who would be the right agency to do this. I've often thought it would be the USGS, but it would be really amazing to pull together all public, private, any information that we have, any borehole, any water table, like pull together all this information. Mm-hmm. And if you look at the map behind you, it looks like a lot of data points until you start to try to build a model of Texas, and there's like giant white space, and you're like, okay, we thought there was a lot of data, but there's really not. And I think that we need to, think about how we can pull all of this data together as, in a common platform, a common framework, and make it accessible as possible. It's not just like piling the data in one place or making an interface to access it. It's really about then going further and saying, okay, well, what are easy frameworks that we can start to connect things together? Or if you have a geostatistical model, or you want to start to build hydrostratigraphy of the US, how do we start to pull these things together? And these are big community agency level efforts that I think would really help us as a country to sort of start to figure some of these things out. Now, they still wouldn't be perfect, because even if you had this kind of a model, you would drill a well and say, okay, these things were okay and these things were way off, and this sandstone was supposed to be here, but it was actually there. But I think the process of then saying, okay, now we can feed these back and update the model and update, our understanding will just be helpful. And then, I think we really need to think about emerging technologies like, aeromag, like surveys there. It is feasible to fly the whole US, and it is feasible to use EM and, fly the whole US. It would not be cheap. My guess is it would be, in the billions of dollars. But if we had, a geophysical survey of the whole US that went down, a couple 100 meters, that could be pretty crazy, right? That could be that in, folding in. And what we really need are some agencies. And I know that at times the USGS has wanted to do this, and it'd be great if this is something they would champion, because these are the sorts of things that we need to do. We need to sort of say, okay, as a community, what's going to like really bridge your scale and my scale? And, and what activities are really going to kind of connect these pieces together?
So when we talk about this kind of modeling, this grand idea of having a model, you know, a couple 100 meters down of the whole US. Like, how can that modeling help when it comes to, you know, water scarcity or, you know, allocations or, you know, a lot of the issues we're talking about?
Sure. I mean, I think it can help a lot. And I think what we need to do is think about, you know, kind of the wish list of what the model, you know, what this sort of thing could do, but then also be more realistic about how accurate the answers are that come out of it, and what the uncertainties are about it. Now, one really nice thing about the modeling that I do is we try to remove boundary conditions. So we're simulating groundwater, but we're also simulating surface water on vadosone, plant processes. We simulate snow, but we don't have boundary conditions where we're saying, okay, we're tuning these boundary conditions and that's how much water is in the model. We're using observed meteorology to say, okay, this is how much it rains, this is, you know, how much ET happens, and this is what contributes to recharge groundwater, you know, the amount of groundwater we have. Now, uncertainty in the subsurface still has a huge role, because if we've got different depths to bedrock, different porosities, that's going to dictate how much storage we have. But because we're conserving water, and we say, okay, well, if it's a drought year, how much does groundwater go down versus ET going down versus stream flow going down? That starts to give you real information to say, okay, how much should we be pumping versus, you know, banking our reservoirs, or how much should we, you know, be thinking about this as a connected system? And I think that's the sort of information that's really useful out of the kind of modeling that I do. But, you know, we're not to the point yet. That's the goal, is to be able to say, okay, we're useful, and you know, what is your, as a farmer, or as somebody who's using groundwater to grow food, or, you know, to supply industry or the public, you know, we have an estimate of how much water is there that's helpful. And that, you know, is the goal. We're not there yet, but I think that that's the idea. And then we could start to say, all right, how much do our large scale water management, you know, particularly when it pertains to surface water or curtailing groundwater, how much does this impact, and what is this going to play out, and does this help us in the long run? Or should we think about some other mix or some other way of regulating and managing this resource?
It's really interesting. You say, you know, the weather patterns and how you're modeling that. 9 years ago, I'm working in Northeast Washington, Republic, Washington, for a Kinross gold mine. And we worked through Thanksgiving up to Christmas because it hadn't snowed. And the entire process of the mine had been based on, when it snows, we shut down and we come back sometime in February. And the hydro up there was saying, this isn't good, guys. This isn't natural. So when you're looking at these weather patterns for your modeling, is it hypotheticals? Is it looking at that? Did you see what was going to happen with California and the Pacific Northwest as it was happening? Since you said you've been doing this about 10 years,
Yeah, I wish. I mean, we do, right? So, I mean, you know, if we could have predicted you know, one of the biggest droughts on record in California, you know, that would be even more helpful. But what we have done is a lot of work to understand, like, how much groundwater did we use, you know, and how do we bracket that? And so, you know, until recently, there's not really a lot of reporting of how much pumping was going on in the Central Valley. And most economic estimates were that it was probably pretty net even. There wasn't a huge economic loss in agriculture in the Central Valley because so much groundwater was pumped, and because, you know, and that's, in some senses, that's great, right? Because groundwater is our buffer. Groundwater is our bank account. We have a really low checking account. You draw down the savings, but then you hope that you're going to be able to bump the savings back up in a wet year. And, you know, trying to understand with, you know, kind of at the big picture, how much we depleted groundwater, you know, and one of my PhD students started to simulate through the drought years, and with a bunch of different pumping scenarios, and then starting to use things like GRACE, like remote sensing products, to say, okay, what's the total water storage change, and what about all these other ways to sort of constrain the model? And you can get some estimates. They're not fine-grained estimates, but they tend to be estimates that say, okay, this reflects how much water maybe we used. And the idea is to say, okay, now how do you better position yourself to respond to these kinds of events. Because obviously, you know, we don't want to say you should never pump groundwater, but obviously you want to say you shouldn't just pump groundwater with wild abandon, because it's finite resource. And it's understanding how we can say, okay, where are situations where maybe we, you know, I mean, obviously there's places where we over depleted, we know that already, but if we want to think about sustainable groundwater use and in the big picture and in the, you know, the sequence of wet and dry years. And so we do a lot to sort of go back historically and use, you know, the drought in California for the past well, it's broken out, but the past 5 years, you know, 2012 to 17, 18, as a measure for a bad drought year. Or we just, you know, you can do things in models that you would never do in the real system. You can create a drought in a model really easily. You can say, all right, well, let's take the same weather, but let's make it a little bit warmer, or let's take the same weather and let's decrease the amount of precipitation a little bit. And you can start to say, okay, how does this shift, and how does this shift all the way through groundwater? Or if, you know, if you have the same amount of pumping, or if you want to change pumping, you can start to run these scenarios that maybe aren't like, you know, they're useful in the way that, you know, a scenario or experiment is useful in informing the decision, not in saying this is exact projection of what's going to happen.
Mm-hmm. So I have one last question before we wrap up here. You had talked about drilling as, you know, a well as a pinprick. And even if I've been drilling in the same area for 20 years and I've, you know, done wells all over the place and I know that area like the back of my hand, like even with that amount of data in my head about a small area, what do the individual pinpricks miss about the big picture?
I think you guys would know the answer to this question better than me, but I mean, you're, you know, it's the, even though you know an area really well, and you know, we can take a really easy example. You've got a fractured bedrock system, and it can be really conductive, can have a lot of water, but depending on whether you're hitting fractures or not, or even whether you're hitting a high fracture density or not, and it can be the same, you know, fractured system and relatively consistent, you know, level of hitting that fractured bedrock, but it's hard to predict a priori where the more fractured areas are and the less fractured areas are. Or if it's an aquitard system, you know, aquitards are usually, you know, unlike what we have in textbooks.
Mm-hmm.
They're thick, they're thin, they go away in spots, you know, they might be leaky. There's all of these details that, you know, depending on, and that can change really, really in short distances. And so having that understanding is great. And, you know, but then it's still unlikely that you're going to say, okay, I know that area is going to be the most highly fractured and it's going to be the most productive. Or I know the aquitard's thickest in that area and that's going to be, you know, the most confined, and, you know, whatever. It's just hard to predict, and these things change rapidly. And so you have these little windows, or these little, you know, pinpricks, if you will, into the subsurface.
Mm-hmm. Mm-hmm. So with that, I think we'll wrap up today's episode. Thanks again, Reed. You know, I'm kind of a certified data nerd, so I find this whole discussion about modeling just fascinating, and what you can, you know, observe about what's out there, what's, you know, hundreds of feet underground with just data. I love that. So Brock, what did you find interesting?
How dynamic our groundwater system is, and how important it is for our collaboration as the contractor drillers to be working with the scientists to give the best data, because one day, who knows if it'll be just our planet, you know, or if we're going to be looking at how we store water on an ASR well on another planet or something like that. So it's all embracing the science is all I want to tell my brothers and sisters in drilling to do, is hug it, don't let it go, pet it, do whatever you have to do, but embrace the science.
Yes,
Awesome.
Wonderful. Well, thanks again to Reed Maxwell. Where can the audience find out more about you, Reed?
So you can go to maxwell.princeton.edu, or if you want to find out about some of the big data, big simulation projects we have two really neat projects. One is hydroframe.org. It's a framework, it's computer scientists and hydrologists to build a national scale water modeling framework. And, there's a lot of neat stuff that we're doing there, including we've built I don't know how many of you've seen the sand tank aquifer model. Looks like an ant farm. So we have a Parflow version of that, runs in gamified interface. We have a dedicated server at Princeton to just run just that model for classroom use. We've had 4,000 users since we launched it in February, and partly I think that's the pandemic because everybody is not able to do anything in person, so it works well. But with a lot of cool stuff like that, and that's a lot of kind of what we're trying to build, and we're trying to make modeling easier and more accessible, and data easier and more accessible. Mm-hmm. So you can go to hydroframe.org, you can check that out. It's a National Science Foundation framework, cyber infrastructure framework project. It's 10 PI, 7 institutions. It's a really big project, but we're doing really neat things, and hopefully eventually, engaging to the level that data nerds or, people who want to really get their hands dirty with these things in a very easy kind of interface way can dive in.
Mm-hmm. Yeah, and it definitely sounds like that sort of thing could, help feed the imagination of the next generation of hydrogeologists.
Hopefully, yeah.
So I just want to see hydros and computer science majors in the same room, because that's a fantastic situation.
That is what we're trying to do. That is one of the goals of this project, is to get hydrologists and computer scientists all on the same team. It's interesting. There's a lot of dynamics, and it's been really fun. It's been really great, but it's been a very big educational adventure. That's for sure.
Okay, well, you can find fresh episodes of the show on our website and on Apple Podcasts every other week. Just search Drilling Insight and hit subscribe. Visit nationaldriller.com for the latest industry news and views, and of course, follow us on the usual social media channels. Until next time, this is Drilling Insight.